In this video, I'd like to talk about the second derivative test, or using the second derivative of a function to find relative extrema. In this case, we're using the function f of x equals 2 sine of x plus cosine of 2x on the interval 0 to 2 pi. Now, what the second derivative test tells us is that, first of all, if certain criteria are met, so if f prime of c is equal to 0. So c is a critical number. Not any critical number. Remember, a critical number is where the first derivative is equal to 0 or undefined. So specifically a critical number where the first derivative is defined. It's equal to 0. And the second derivative, f double prime of c, is defined at c and around c. So at and around x equals c. So that means the second derivative exists on an open interval containing c. Then, what the second derivative test tells us is, well, one, if the second derivative is positive when x is equal to c. So f double prime of c is positive, meaning the graph is concave up. That implies f of c is a relative minimum. Now, why is that? Well, if the second derivative is positive, the graph is concave up. And if the first derivative is 0, there is a horizontal tangent line. And if those two things happen, then you have a minimum occurring. And by that same logic, if the second derivative is negative when x equals c, that implies f of c is a maximum. So by that same logic, if the second derivative is negative, the graph is concave down. And then if the first derivative is 0, the tangent line is horizontal. So we have a maximum value. Now, this doesn't account for all possible values of c, right? If the second derivative is positive at c, we have a minimum. If the second derivative is negative at c, we have a maximum. But if the second derivative is 0 when you plug in c, the test fails. It doesn't tell you whether or not you have a relative max, a relative min, or neither. So in that case, we would say use first derivative test. Okay, so this is the one drawback with the second derivative test. It usually works, but occasionally it doesn't work if the second derivative equals 0, because we're looking for positive second derivative, we have a minimum. Negative second derivative, we have a maximum. All right, so let's look at the function f of x equals 2 sine of x plus cosine of 2x. So let's start off by taking the derivative of this function. So f prime of x is equal to, well, the derivative of 2 sine of x would be 2 cosine of x. The derivative of sine is cosine. And the derivative of cosine is negative sine. We have to apply the chain rule because we have this 2x in here. So that'll be negative 2 times the cosine. Or sorry, negative 2 times the sine of 2x. And we have to set the second derivative equal to 0. Now, we have an issue here. One, the cosine function has an angle of x, and the sine function has an angle of 2x. So it makes it difficult to solve this algebraically when you have different angles, but we could fix that by applying the double angle formula for sine. And we know that the sine of 2x is equal to 2 times the sine of x times the cosine of x. And that's our double angle formula. So let's apply that. 2 cosine of x minus, well now there's already a 2 there, plus another 2 from the double angle formula, so it'll be 4. 2 times 2 is 4. Sine of x cosine of x is equal to 0. And we have a cosine of x in the first term. We have a cosine of x in the second term. So we could factor out that cosine of x, and actually we could factor out a 2 as well. So 2 cosine of x, and we're left with 1 minus 2 sine of x is equal to 0. Okay, great. So now that it's in factored form, this first factor, 2 cosine of x is equal to 0, and cosine of x equals 0, or when x is equal to, well, when is the cosine function equal to 0? Well, that's at pi over 2 and 3 pi over 2. And then 1 minus 2 sine of x equal to 0. Well, if we solve for the sine of x, we'll have when is the sine of x equal to 1/2, and that happens when x is equal to pi over 6 or 5 pi over 6. All right, so these are our critical numbers. We have 4 critical numbers. 1, 2, 3, and 4. These are our critical numbers. So now we want to know what is the second derivative look like at each one of these critical numbers. Is the second derivative positive, or is the second derivative negative? Okay, so what we want to do is critical number and second derivative. So let's see. Let's put these in numerical order. So the pi over 6 will come first, then the pi over 2, then the 5 pi over 6, and then the 3 pi over 2. So we're basically plugging these critical numbers into the second derivative. All right, so second derivative. Let's come down here. We'll switch up colors. So the second derivative, so remember we're taking the derivative of the derivative. The second derivative, the derivative of cosine of x is negative sine of x. So that's negative 2 sine of x. And using the chain rule again here, minus 4 cosine of 2x. All right, so that's our second derivative. Now we're plugging, we need to figure out what is f double prime of pi over 6, f double prime of pi over 2, f double prime of 5 pi over 6, and f double prime of 3 pi over 2. Right, so we're plugging those critical numbers into the second derivative. All right, so if we plug pi over 6 into the second derivative, well, let's stick with the red. That will be a negative 2 times the sine of pi over 6 minus the 4 times the cosine of 2x. So the cosine of 2 times pi over 6 is the cosine of pi over 3, which is 1/2. So if we plug pi over 6 into our second derivative, we get negative 3. So second derivative is negative which means we have a maximum value occurring at x equals pi over 6. And if we plug pi over 2 in, we'll have a negative 2 times the sine of pi over 2, which is 1, minus the 4, times the cosine of pi, which is negative 1. So we'll have a negative 2 minus a minus 4, negative 2 plus 4, which is 2. So we have a positive value at pi over 2, which means the function has a minimum when x is equal to pi over 2. All right, and that's it. Just keep repeating the process for each of the critical values. Third critical value is 5 pi over 6. Plug that into the second derivative. We'll have a negative 2 times the sine of 5 pi over 6, which is 1/2, minus 4 times the cosine of 5 pi over 3, which is positive 1/2. And so if we crunch those numbers, we'll have a negative 3. So when we plug 5 pi over 6 into our second derivative, we get a negative number, which means we have another maximum value when x is 5 pi over 6. And if we plug in 3 pi over 2, we'll have a negative 2 times the sine of 3 pi over 2, which is negative 1, minus the 4 times the cosine of 3 pi, which is negative 1, and that will give us a positive 6. And when the second derivative is positive and the first derivative is 0, we have a minimum value. All right. And so those are the locations of the relative extrema. So those are the x values. So basically, we need to now, we have a max of blank at x equals pi over 6. We have a minimum of blank at x equals pi over 2. We have another maximum blank when x is equal to 5 pi over 6, and then we have a minimum of blank, we still don't know, when x is equal to 3 pi over 2. All right, so we have to plug these x values back into the original function, f of x. And the original function was the 2 sine of x plus cosine of 2x. And so we need to figure out what is f of pi over 6. If we plug in pi over 6 to the original function, we'll have 2 times 1/2 plus 1/2, which is 1 plus 1/2, or 3 over 2. All right, we plug the next x value in, f of pi over 2. Again, we need the y values of the original function. So that's 2 times 1 plus a negative 1. Sine of pi over 2 is 1, and the cosine of pi is negative 1. And so 2 minus 1 is 1. And so the minimum value of 1 when x is pi over 2. And the same thing, we'll have to plug in 5 pi over 6 into our original function, and we'll have to plug in 3 pi over 2 into our original function. So this is the 3/2. This is the 1. If we plug in 5 pi over 6, we'll have a 2 times a 1/2 plus a 1/2, which is, again, 3 over 2. So remember, our extrema are the y values. The critical numbers are the locations, or the x values are the locations of those relative extrema. And finally, if we plug in 3 pi over 2 to our original function, we'll have a 2 times a -1 plus another -1 for a total of -3. Okay, so these are our extrema, and these are the locations of those relative extrema. So we have a relative maximum of 3 over 2. It's the y value at an x value of pi over 6. All right, that about does it for this video. I hope it was helpful.